Section 4 looks at taking a number of samples, and then for the particular parameter that you're interested in, taking the mean for that parameter from each of those samples. When we look at the sampling distribution of the mean, in other words, we have done the mean of a number of samples and then taken the mean of all those sample means, we find the distribution of sample means tends to be a normal distribution. For example, if you roll a die 5 times and find the mean, and do this repeatedly and find the mean of each of those samples, the mean of those sample means will follow a normal distribution. If we do the same for the variance, the distribution of sample variances with all samples again having the same size, taken from the same population, the mean of the sample variance is the population variance. So note, for both of these cases, the variance and the mean, when we take the mean of a whole bunch of sample means, or the mean, average, of a whole bunch of sample variances, they match the mean of the population or the variance of the population. Note in this case that we're using variance instead of standard deviation because of that square root, and that would mess us up there. Now, the formulas for standard deviation and variance, of course, we have seen before. Notice that it's just n in the denominator because now we're dealing with a population and not a sample. So, continuing on, what if we're talking about a proportion instead of the mean or a variance? The distribution of sample proportions, called p hat, with all samples again having the same size, taken from the same population, the mean of the sample proportion is the population proportion. So in all these cases, the mean of these things matches what you would have from the population. And they tend to be a normal distribution. And if they're a normal distribution, then that means that we can use our z-scores to find our probabilities. Now, not everything works this way. When they do not target the population parameter when repeated indefinitely, such as median, range, and standard deviation, though the bias is less than in some of the other ones for large samples, that means then it doesn't match. It's going to be a little bit too small or a little bit too big when we do the mean of these other parameters. And so we would call them biased estimators. So this leads us to what's called the central limit theorem. And basically, for all samples of the same size with n greater than 30, the sampling distribution of the mean, sample mean, can be approximated by a normal distribution with a mean mu and a standard deviation of sigma over the square root of n. This means the original population can have any distribution, uniform, skewed, bimodal, but the distribution of sample means can be approximated by a normal distribution when n is greater than 30, which means that distribution of sample means can then be converted to z-scores. If the distribution is a normal distribution, then you do not need that requirement that n has to be greater than 30. But it could be something else, and as long as n is greater than 30, then the distribution of sample means can be approximated by the normal distribution. So, a little bit of vocabulary here. This is the mean, mu. Remember, mu is used for population. So this is the mean of the sample means will equal the mean of the population. And then here, the standard the variance, the standard deviation of the sample means, will equal the standard deviation of the population divided by the square root of n. And then the z-score conversions for these things would look like this. And again, it's very similar to what we had before. We would have had x bar subtract mu over sigma, but now we have changed that to x instead of x bar, because we're doing a mean of a sample, subtracting the mean of the means over the standard deviation of the means. And again, these equations also apply if n is greater than 30, but do not apply if n is less than 30, unless it is a normal distribution, or approximately normal distribution in the first place. And so, really what this section comes down to is, are you doing a probability for an individual value, or are you doing a probability for the mean of sample values? And so they look very similar. The difference, of course, is these ones are all about means. This one is about an individual value. A little bit confusing, but we're going to look at some examples to help us out. So first thing we're going to look at is we have the ages here and years of 4 U.S. presidents when they were assassinated in office. Their ages were 56, 49, 58, and 46. So, assuming 2 of the ages are randomly selected with replacement, list the 16 different possible samples, and you can see they're listed here. Now they're listed in a kind of order, but randomly any one of those could be selected. And we want to find the mean, median, range, and variance of each of the 16 samples, and then summarize them in probability tables. So first off, to get the mean, of course, you add the 2, divide by 2. The median is the same thing, so this is why we have mean and median. Since there are only 2 numbers, mean and median would be the same. If we went to 3 numbers, they would not necessarily have to be the same. The range, of course, is just the smallest one, subtract the biggest one. When they are the same, you're going to get 0, but like 46 to 49, the difference is 3, 46 to 56, the difference is 10, and so forth. And then the variance, of course, we get the variance by taking each of these numbers, subtracting the mean, and then we square it, and we're going to divide by n in this case, well, actually each sample, so n minus 1, and because n is 2, 2 minus 1 is 1, so basically what you're just looking at is the difference from the mean, and then you have 2 numbers, so you'll have 2 differences. And since this is halfway between, you end up with the same thing twice. So for example, 46 subtract the 47.5 would be 1.5. You square the 1.5 and you get 2.25. 49 subtract the 47.5 is 1.5. 1.5 squared is again 2.25. You have 2 of them, so 2.25 plus 2.25 gives you 4.5. Or we'll do one more here. 46 subtract the 51 is negative 5, but negative 5 squared is 25. 56 subtract the 51 is 5, but again 5 squared is 25. 25 and 25 gives me the 50. Remember, the difference between variance and standard deviation is the square root part. And so we have done mean, median, range, and variance for all of these samples. Okay? And then we put them into a probability distribution. So here are all the different means, or medians if you want. Here are the different ranges that we had in the list. And then here are the different variances, s squared for variance. Now, following that is the probability. In other words, how many times did it occur out of the 16 possible chances to occur. So, for example, there's only 146 in the entire list, So just 1 out of 16 would be its probability if that particular sample was randomly selected. On the other hand, there are a couple of 51s, and so that was 2 out of 16. In other words, you'd have twice the chance of getting a 51 randomly than you would a 46. Did the same thing with ranges. There are 4 zeros, so the chance out of the 16 of getting a 0 would be 4 out of 16. And then here are the variances. Now, to find the mean of these frequency distributions or probability distributions, all we had to do was just basically multiply and then add them up. And so when you multiply each one of these times its probability and then add them all up, the mean of the sample means was 52.25. The mean of the sample ranges was 5.375. And the mean of the sample variances was 24.1875. And again, all you have to do is go this one times this one, plus this one times this one, plus this one times this one, and so forth. Now, if it was just a frequency distribution, then you would divide by the sum of the frequencies. But since this is a probability distribution, when you add up all the probabilities, you get to 1, and so divide by 1 isn't going to change anything. So, here we have all our samples, 16 possible samples, and we have found the mean, median, range, and variance for each one of the samples, and then we have constructed probability distributions for each one of those, and then found out the mean of the samples, mean of the mean of the ranges, mean of the variances. Alright, so now we want to compare what the population parameters with the means of the sample parameters would look like. Okay, so for a population, we got 4 numbers. We got basically 49, 46, 49, 56, and 58. So to find the mean, we just add the 4 up, divide by 4. For the standard deviation, or excuse me, for the variance, we add them up, no square root, so it's not standard deviation. We add them up, add up the differences squared, divide by 4, we get this. Range, well, the smallest one is 46, the biggest one is 58, so the range is 12. And the median, I've written these in order, so the middle 2, divide by 2, gives us our median. Okay, now, how do these compare? Well, for the means, the same thing. Medians, not the same thing. Range, not the same thing. Variance, the same. So, this is an illustration of how the mean and the variance for the population matched the mean of the sample means and the mean of the sample variances, the things that we got up here. So again, the mean of the sample means and the mean of sample variances target, which means matches, the population mean and the population variance. However, the median and the range, those parameters did not match. They would have been biased. Now, let's look at some uses of the central limit theorem. So, suppose an elevator is rated for a maximum capacity of 16 passengers with a total weight of 2,500 pounds. The mean is 182.9 pounds, and the standard deviation is 40.8 pounds for the male adults. So, what is the probability that one randomly selected adult male has a weight that's greater than 156.25, which would have been the mean for those 16 passengers weighing 2,500 pounds? So, we got 16 people. We're going to pick one randomly. The question is, what's the probability that that one we picked randomly would have a weight that was greater than the average of the whole group? Well, since we are dealing with an individual value, we're going to use table 4. Just like we would before, we're going to find our z-score. Z-score comes out negative 0.65, which when we use table 4 will give us 0.2578. Remember, the table always goes to the left. We want to find the situation for more than the average, so we have to subtract, and we end up with a 74.2% chance of randomly selecting one male adult that will weigh more than the average of those 16 people. Now, in part B, we're going to kind of do the same thing, but instead of selecting one person, we're now going to select a sample of 16. And the question is, what's the probability that a sample of 16 randomly selected male adults has a mean weight greater than 156.25, which means that altogether they would exceed the 2,500 pounds, which is what the elevator is rated for. So this is not an individual case, this is a sample, and since we are dealing with a sample, we need to do, or with the mean of the 16 passengers, we're now using the central limit theorem first. Now, we do not have n greater than 30, but we're going to assume that the weights are normally distributed. That's not necessarily true, but we're going to assume that for this case. So, we don't go right to our z-score. We first have to find the mean of sample means, which is just the mean of the population, so it matches. This one will always match, 182, 182. But for the standard deviation, note how we have to divide the population standard deviation by the square root of n, and we end up with 40.8, which was our standard deviation for the population, divided by the square root of 13, and we'll get 10.2 for that. Now we can go find the, if you will, adjusted z-score using these new values for the mean of sample means and the mean of the standard deviation. Plug them in, and we get this value here. And this gives us an area of 0.0045 to the left, which when we then subtract from 1 gives us 0.9955 to the right, which would say, in this case, there is a 99.6% chance that the total weight of the 16 passengers will exceed the 2,500 pounds. So, really, two different ways to look at potentially the same problem. In the one case, it's, what's the average weight of one individual? In the other case, it's like you're going to combine the whole group, and so what will the total on average be? And so in the one case, part A, we used z-scores just like we were doing before, earlier in the chapter. But in the second case, since we had a sample, we were using the fact that the mean of the sample means equals the mean of the population, and therefore we could use the central limit theorem to find out the chance that this would be true. Now, let's try a second example here. Suppose the sitting height for a male 5-year-old has a mean of 61.8 centimeters and a standard deviation of 2.9 centimeters. Compare the following probability for desk height. So first we're going to say the sitting height will accommodate 95% of all boys. So note, we're going to actually go backwards from what we did in the previous problem. We want to find out what height would be necessary to accommodate 95% of all boys. For an individual desk, 95% to the left, because we want to be more than that, would be a z of 1.645, and then using our, basically it's just the z-score formula rearranged to find x, we find out that x would be 66.6 centimeters. In other words, at that height, we're going to accommodate 95% of all the boys. Okay? Now, what about the sitting height, we will accommodate 95% of the means for sitting heights of randomly selected samples of 25 boys, or approximately a classroom, an elementary classroom full of boys. Well, now we're going to have to find the mean of sample means, which is just the mean of the population, and the standard deviation of sample means, which is the standard deviation divided by square root of n, which in this case came out to be 0.58. And note, this is always going to be less than the other one, since we're dividing by something. Plug them all in, and we end up with 62.8 centimeters. Now, only one student can fit within one desk at a time, so the average doesn't really matter. In other words, if we had an average of 62.8 centimeters for our desk heights, that would accommodate the 95% of all boys. But since only one student can fit within one desk at a time, the average height doesn't really matter. What matters is that all of them, 95% of them, can fit within. And so we would definitely want to do part A as opposed to part B in this case. Whereas in the previous example, we'd really rather worry about what would happen as a group. Would it exceed what the elevator could handle, than whether or not one individual was more than average. All right, one last example. We have filled Coke cans. They have a mean of 12 ounces and a standard deviation of 0.11 ounces. A random sample of the 36 Coke cans has a mean of 12.19 ounces. Okay, so they randomly selected 36 cans, and it had a mean of 12.19. What is the probability? A sample of 36 cans will have a mean of 12.19 ounces or greater. Interpret the results. So again, since we have a group, 36 cans, we're going to use the central limit theorem. We're going to modify our equations. And so the mean of sample means equals the mean of the population, which was just 12. The mean of the standard deviations, we come out with 0.11 over the square root of 36, which of course is 6. So we get 0.01833 for that one. Plug them in to find our z-score, and we come out with 10.36, which is an extreme number of standard deviations away from the mean. And in fact, since it's past the 3.5, we just say 0.9999 to the left, which when we subtract from 1, because we wanted to know 12.19 or greater, that's why we had to do the subtract part, we come out with 0.0001, so basically less than 1% of 1%. So the chances are extremely small that a mean of 12.19 ounces would occur if the population mean of 12.0 ounces is correct. So the population mean is likely a little bit higher than 12.0, but not much, because after all, the sample was 12.19. So it's probably not exactly 12.0, but it's not very far above it either. So a quick introduction into looking at the central limit theorem and taking the mean of sample means and seeing how that plays out.